Hello, everyone. We are working on Chapter 2, Section 2.5 that talks about calculating power and minimum sample sizes. So we could set up a situation where we set our alpha level. Let's say alpha is 0.05. And then we can get our Z alpha using Q norm. Now remember, Q norm says for a given area, what is the value of Z associated with that area? And in our case, we're using the upper tail probability to then define that. And so I have to say lower dot tail equals false, so it knows that I want the positive Z score. Okay, so if I run this through, then I can get Z alpha of 1.645. And then I can set up my beta, or the probability of a type 2 error, to be 0.1. And I would like to get the value for Z when beta equals 0.10. And so by doing this, sorry about that, I can use the Q norm function again to calculate my Z beta. All right, 1.28. Now, the book gives an example where we have a hypothesized proportion of 0.06, and then we observe a proportion of 0.02, and we can then get Q0 and Q1. All right, I can read those in just so that it is available to me. And I can also say, I don't know what my sample size is yet, but if I got these values and I could look at N anywhere between 1 and 250, right? N is between 1 and 250. If I observed this going on, what would my p-value be? So I'm going to first calculate my test statistic here, and then I'm going to calculate the area associated with observing that test statistic. So I'm going to do p norm of whatever I calculate. So here I get all of my p-values for those particular values of N. And if I want, I could plot this. So I'm going to plot if my sample size was 1 and I got P1 and P0 of these numbers, what would my p-value be? If my sample size was 2, what would my p-value be? And so on and so forth. So you can kind of see the relationship that essentially, if you observe the same exact thing in your sample, right, but your sample size gets larger, the p-value is going to get smaller and smaller because it's going to be more and more obvious that your hypothesized proportion is wrong, right? If I only take a sample of 2 people and I see a particular thing in my sample, I don't have a ton of evidence to say that the null hypothesis is wrong. But if I take 250 people and I calculate the probability of observing a test statistic as or more extreme, given I saw so many people and I saw this small of a proportion compared to what I expected, right? Then the p-value is getting smaller. So one thing to note is that, right, I can always get small p-values as long as I just take a bigger and bigger and bigger and bigger sample size. That's why we should also think about what's the right sample size I should be taking to be able to observe a certain effect. All right, you can set up your rejection region as well. There's a formula for the rejection region in the book. It's N times the hypothesized proportion minus Z alpha times the square root of NPQ, okay? So essentially, for a given sample size, right, when am I going to reject, right? So let's suppose that we have 250 people in our sample. Essentially, I'm going to reject whenever I see 8 or less successes out of those 250. That will lead to a rejection. So it's nice to understand, like, at different values, I might see a different number of successes. Okay. And if I wanted to calculate the power, there's a nice formula for power. So let's see how power and sample size are related. All right. So here, as my sample size increases, power also increases. So essentially, if I was doing this and I wanted a power of like 90%, right? I'm really not achieving that until I have around 200 people, right? So if I want to say a priori, if I want to see an effect of a certain size, how many people do I need if I set up a particular alpha level and I set up a particular beta level? How many people do I need to take to be able to have a certain level of power to observe a certain effect size? So this is really in the planning stages of your study. All right. Now let's talk about calculating sample sizes, because in all these cases, I said, suppose I took samples of all these different sizes. What do things look like? But I can first calculate my z-score associated with 0.05, right? 1.645. And I can get my beta. If I want 90% power, then my beta, my probability of type 2 error is going to be 0.10. Okay. I have the same setup of my hypothesized proportion versus what I saw in my sample. And there's some formulas in the book. Remember that we always round up for sample size. So that's why I'm using the ceiling function. The ceiling says no matter what you get, round that number up. Okay. And then I'm just using the formulas in the book to calculate the minimum sample size required based on all the information that we have here about what our alpha level is, what our beta level is, and what are hypothesized versus the size of the effect that we might see. By doing that, we see that we need 204 people. Now that lines up really nicely with the graph that we saw before, which showed us what is in and what is power. But remember, by the time we wanted to get 90% power, we need 204 people in our sample. Now there's a shortcut formula in our book that calculates in prime. And by doing that, we get the value of needing 228 people. And then there's one more formula that says you can also use this shortcut to be able to calculate in, and it says 229. So essentially these are pretty much agreeing with each other. We need around 200 people to be able to have the power that we're looking for to see the effect of a difference of 0.04 between the 0.02 to 0.06. So a pretty safe bet for how many people I need in my study is it's anywhere between 204 and about 230 people. Okay, if we have a two-sided test, we're going to calculate this slightly differently, but the formulas are very close to being the same. The only difference is we have the Z alpha over 2, where instead of the tail area for alpha being 0.05, now we have 0.025 on each side of the curve. Okay, so if we're doing a two-sided test, then we need 285 people in our study. All right. The next part of this chapter, we do sample size for confidence intervals. And there are some shortcut formulas. And these are approximations for how big of a sample you would need. So we're going to be in the case where sample size for confidence intervals. So we have a two-sided test. So we set up our alpha level, and then we get our Z alpha over 2. We set up what we saw in our sample, right? And what we saw in our sample was 0.02. Our hypothesized proportion was 0.06. And suppose we didn't want our interval our complete width of our interval to be any bigger than 0.2. Right? So we want to limit the width of our confidence interval because we want to be able to say that with a certain amount of certainty, I am pretty sure that my parameter is within these two values. And I don't want a huge interval because then I'm not going to have a very good idea of the estimate. If D is too big, then I don't have enough information to make some decisions. So I want to limit that to be width of 0.2. All right. By doing this and following the formulas in the book, there were 3 different values of K that we could see. And those choices of K depend on the table in the book, but I just put all 3 here, right? We're either going to have K in this situation to be 0.64, 0.66, and 1. But if you go back and you read the relationship of D, we're really going to be focused on this first K. But I just wanted to have all 3 in case you're in one of the other situations. All right, so once again, we're going to use the ceiling function for n because we want to round up. And in the book, it mentions that if we're doing something without the continuity correction, the sample size should just be the first term. And that's what we have here. Okay, so that would look like we need about 62 people. All right. If we use the continuity correction and estimate in the book, then we would say that we need 72 people. I did this by hand because I was making some derivations and I got something slightly different. Mine's a little more strict, saying I think we need about 104 people. And there's one more formula that if you base your confidence interval on that lower upper and upper bound in 2.17 and 2.18, then you would need anywhere from 70 to 103 people. So these formulas and where you would use them are all mapped out in the book, but I just wanted to be able to show you that you can easily code this in R, and I'm going to provide you with this code. And it's more just about knowing which situation you're in, but in reality, we're just trying to plan like how many people do I actually need to sample to be able to observe a particular difference for a hypothesis test, or to be able to limit the size of my confidence interval, limit the width so that I have a really accurate prediction with not too much variability. How many people do I need to take to be able to get to those estimates and being able to have a very tight confidence interval? So I hope you learned something today, and I will see you next time.